Data science has been becoming a growing profession and is also the heart of many organizations. That's why Data Science Portugal was born. The first community created by data scientists for data scientists. DSPT wants to gather anyone who works in the field and chat about any topic over this great subject. All members from our team are committed to make sure that the data science field evolves in a healthier and stronger way. To ensure that the focus is on sharing knowledge, we guarantee that our stage is not a place that supports any commercial or recruitment content, and our kind speakers are committed to share their experience for free. We want you. Let's do bigger things together. Join us at any event all around Portugal or online.
Hi everyone, and welcome to today's webinar. My name is Isabel. I have Mario here with me, and we'll be our hosts. Hi Mario. So today we are going to have the following agenda. We are going to do the usual introduction of DSPT. Then we're going to our talk by Inês Pereira, followed by a short Q&A, and we are still trying on the networking. You already probably saw all of our spam and links regarding Discord. So join us at the end and we can have a nice session. So regarding the DSPT, as most of you already know, we are an informal community of data science enthusiasts, and we want to promote knowledge sharing and experience. We have been doing meetups for a long time ago. So regarding our philosophy, we want to promote knowledge sharing. Like I said, we organize open events and we try to promote networking online and offline. But we already have some things that we don't want you to do in our talks, like do selling or promotions, things like that. So have that in consideration once you propose your topic to be here with us. So if you have an idea, if you kind of want to share with all of the community, please use your call of proposals. We'd be happy to have you with us. So where are we? You can find us in Aveiro, Braga, Coimbra, Lisboa, and Porto, and now online on our website on datascienceportugal.com. And our community is also on Slack. Join us on Facebook, on Meetup, on LinkedIn, and now on Discord. So do not forget to join us.
Before presenting our speaker, we want to thank Bosch for sponsoring this webinar. And today we'll have three types of interaction, or we'll try to have three types of interaction. First, the speaker will ask the audience two questions during the presentation, and we ask you to reply with your opinion in the chat, and we will show the top three opinions for that question. Second, we have the typical Q&A. So during the presentation, please ask any question that you have in the YouTube chat. We'll compile the questions and we'll do the discussion after the presentation. And finally, we'll have some minutes, around 30 minutes of time with the speaker in the Discord channel that we have provided. I want to thank Inês Pereira for being here and presenting for us. Inês is connected already. She is a doctoral student at Zurich and is an avid learner and a part-time blogger. So thank you for being here and making time to do a presentation for us and the community. The presentation will be named More Interpretability in Healthcare, and we are very happy to hear from you. So the stage is yours.
All right. Thank you so much for the kind introduction. It's my pleasure. So thanks a lot for having me. And well, let's just get right to it. So I'd like to start out this talk with a disclaimer on what this talk is not going to be. So this talk is not going to be a talk on bleeding edge methods in the realm of machine learning and interpretability. What I want to do is provide food for thought and have a conversation on the topic with you so that you leave this webinar with a more nuanced perspective on what model interpretability means and when and why it is needed. In addition, I also want to tell you a little bit about the line of research I'm in and hopefully convince you that computational neuroscience and translational neuromoduling are, well, first of all, fascinating and more importantly, promising avenues. So just to give you an idea of who I am and why I went for this topic in the first place, so like I said, I work in computational neuroscience, more specifically in translational neuromoduling, meaning I strive to use models to answer clinically meaningful questions related to psychiatric and neurological disorders. And in my research group and line of work, we do give a lot of importance to model interpretability. At the same time, I'm also an MD, so I'm a physician by training. And so the subject of interpretability is quite close to my heart. It's something that I find very important. Okay, so as most of you probably know, there has been in the last few years quite some hype around neural networks and around machine learning and healthcare. And just to give you a few famous examples, in 2016, a group led by Google researchers used the convolutional neural network architecture to detect and evaluate diabetic retinopathy using retinal fundus photographs. In 2017, Esteva and colleagues from Stanford University used a pre-trained CNN to identify more than 750 types of dermatological lesions. In the same year, the FDA approved the AliveCore deep learning algorithm to detect atrial fibrillation, which was used on the Apple Watch. And of course, let's not forget AI and radiology. So all this hype, and especially the claims of superhuman performance, have led to important debates on the topics of model development, model validation, how to deal with bias, how to address the issue of model interpretability, with heated debates taking place both live as well as online. So take this tweet by Geoffrey Hinton from February last year, for example. As you probably all know, Geoffrey Hinton is a major figure in the deep learning community, initially mainly known for his work on backpropagation. So the tweet reads, suppose you have cancer and you have to choose between a black box AI surgeon that cannot explain how it works, but has a 90% cure rate, and a human surgeon with an 80% cure rate. Do you want the AI surgeon to be illegal? So I'll let you react to this if you haven't seen it before. And what I want you to do is to use the YouTube chat now to tell me what you think of this tweet and whether you have any comments or questions that pop up. So I'm just going to turn to the other screen that I have to monitor the chat and see if you have anything coming in. Okay, so I don't see any comments coming in. Is that a black and white view? What about the shades of gray? I guess what you're trying to point at is that, thank you, Pedro, by the way, for that intervention. I guess you're trying to point that there might be some form of middle ground, and I totally agree. I'll get into that as well. I want to have, oh, okay, we have someone saying, I want to have the highest chance of survival. I guess this is also something we'll briefly discuss afterwards, because in medicine, you actually don't just optimize survival. You optimize a lot of things, including quality of life. Okay, so Tiago says AI is trained with data labeled by humans. Therefore, this is somehow a fallacy. Who performed the annotations in the first place? So I guess what you're trying to get at is that we really need to analyze the quality of the data set. And I totally agree with that, because if you know how the data set was generated and what this data set looks like, you can possibly uncover biases and also kind of like assess then whether the model generalizes or not. So good input. Can we choose both? Mm-hmm. Okay, so Marco has an extreme example, but that kind of points out one of the points that I also want to make. If I have cancer in my arm and this AI surgeon decides to cut off my arm, so he would actually then achieve a very high cure rate. But then again, what we were talking for, what about quality of life, right? So good input there. All right. Okay. Okay, so if you don't have any new inputs coming in, I'll just also kind of now give you my perspective on this matter. All right, so, oh, sorry, small glitch there. Okay, so the first question I would ask is this really a dichotomy? And like I said before, I don't think so. I think there are shades of gray in the middle, and it shouldn't be AI surgeon versus human surgeon. It shouldn't be one versus the other. And this narrative is actually quite harmful and non-productive because it leads to defensiveness on both sides. And so AI surgeon and human doctor ideally would cooperate to beat either AI or human alone. Another point we've also touched upon, and another important question, is how do you define success? So in this tweet, the only metric used is cure rate. But what about postoperative complications? What about patient well-being? What about quality of life, right? Okay, so let's try and move on to two other examples. Let's take tumor segmentation, where you want to develop a model that correctly identifies brain tumors versus an algorithm that outputs diagnoses and prognoses. So from the point of view of the user, in this case, the physician, where do you think interpretability is most needed and why? I'll also let you think on this for a few seconds. Again, feel free to use the YouTube chat. And again, let me know which situation you think interpretability is needed the most, and also tell me why you think that. That would be also helpful. I'm going to turn again to the second screen. No opinions? This is more of a poll, so just feel free to type either tumor segmentation or diagnosis and prognosis, because I just want to figure out where the audience kind of stands. Okay, so I'm not getting any input from the audience, so okay, now I am. Okay, so a lot of people are saying diagnosis and prognosis. Some people saying both things are important. Okay, really cool. So can someone now tell me why they think, for example, tumor segmentation would be more important, or why diagnoses would be more important? Why would it be more important to have interpretability in that case? So Pedro says segmentation by itself gives you a feedback, diagnosis only the final class. That's true, and I'm going to get into that. Okay. Okay, well, I think I've gotten now an idea of where the audience stands, so I'll just now give you my perspective on this. And so to answer this question, I would argue that you need to ask more questions, or at least make a few observations. And in this case, one question that I find particularly important is, does the model make easily verifiable predictions? So put differently, can the human, the physician in this case, easily identify mistakes? And I would argue that a radiologist can much more easily visually verify whether the model did a good job in identifying the tumor or the suspect mass. It becomes much harder to rigorously evaluate the model at a much more highly dimensional and even multimodal problem, where you might have to process and combine information from the clinical interview, the physical examination, several different types of diagnostic tests, and physiological measures. But then again, why are we striving for model interpretability in the first place? So who are we thinking of? And let's take the tumor segmentation example again. So don't get me wrong, I think situations like these can be harmful. Radiologists are busy enough without having to correct models. But let's imagine the best scenario and the best case scenario, and that the radiologist easily spots the mistake, corrects the segmentation, writes his or her report, and proceeds on with his day or her day. What about the developer of the model? How is he or she going to troubleshoot and figure out why the model was making those false predictions? So the developer has no way or no easy way of guessing what might be going wrong, and therefore has little ground to stand on to improve this model. So my point is that even if the lack of interpretability isn't a problem for the clinician, it ends up being an issue for the model developer working in the back end. Okay, so we have already talked a little bit about interpretability, but we still haven't agreed on a definition. So what's the definition of model interpretability? Well, the reason I've put definitions between quotation marks is that there is no mathematical definition of interpretability, even though several non-mathematical definitions have been proposed. One that is often mentioned is this one from Tim Miller's 2019 paper in Artificial Intelligence, and it reads, interpretability is the degree to which a human observer can understand the cause of a decision. Okay. So even though we are not operating with rigorous mathematical definitions, there is an important distinction that we also need to make. And that distinction is that interpretability is not the same as explainability. Some papers equate interpretability with understandability or intelligibility. That is, that we can grasp how the models work. And in these papers, understandable models are often called transparent, while incomprehensible models are called black boxes. Explainability, on the other hand, is concerned with post hoc interpretations. And examples of post hoc interpretations include verbal explanations of why the model came to a certain conclusion, or saliency maps that are used to analyze deep neural networks. The thing is, this explanation is just another layer of modeling on top and does not make the original black box transparent, as opposed to inherently interpretable models. And just to make this point clear, let's look at an example of a saliency map. Let's say you have the following image of a husky, and you want your classifier to tell you what it is. So a saliency map can be useful to identify areas that are not being considered. But if you seem to be considering the right area and are still making false predictions, you end up not knowing what your model is doing with that part of the image. And in this case, you don't know why the model decided to predict a musical instrument instead of a dog. So what I'm trying to say is that for high-stakes situations, which healthcare is definitely a part of, model interpretability, more than model explainability, ends up being a must for many healthcare challenges. In addition, what is particularly important is that interpretability can help further understanding and uncover potential biases. So in a sense, interpretability can actually be better for accuracy. You could question the model and make it evolve. You could impose constraints if it detects unwanted confounds, etc. You basically open up the ability to probe and to ask questions. On top of all of this, healthcare is more than just dealing with physiological or pathophysiological variants and changes. Patients often want to understand their disease, why they have it, and what all the exams of the jargon mean. So keeping highly trained professionals in the loop, doctors, nurses, is fundamental. Let's not forget the care in healthcare. Okay, now let's go back to this point here, the second point here on the slide. And this might sound a bit abstract right now, but actually, model interpretability can become part of the diagnosis. And this is a particularly promising idea in the field of psychiatry. I'll explain what I mean by all this, but because we're now going to enter a sort of new chapter in this presentation, I'm going to have to provide a bit of context again. So first of all, psychiatry is the medical specialty that is devoted to diagnosis, prevention, and treatment of mental disorders. And these disorders include disorders such as depression, autism spectrum disorder, bipolar disorder, and schizophrenia. The other thing I need to remark is that psychiatry as a field currently faces major challenges. This is because psychiatric disorders are broad and heterogeneous syndromes, where a syndrome is defined as a cluster of symptoms which are subjective and signs which are objective, which consistently occur together. And to explain to you what I mean by heterogeneity, let's take depression as an example. I've put down on this slide an excerpt of the DSM-5 diagnostic criteria for a major depressive episode. The DSM-5, or Diagnostic and Statistical Manual of Mental Disorders, 5th edition, is a diagnostic manual published by the American Psychiatric Association. It is the main tool used in the US, while the World Health Organization, ICD-10, is more widely used in Europe. So back to DSM-5. Again, these are not the full diagnostic criteria, but will help me make my point. So like I said, this is a very busy slide. I don't want you to read everything on it. I just want you to note that of this list of 9 types of symptoms, you need to have 5 or more during the same 2-week period, and one of them needs to be either depressed, mood, or loss of interest. And this already in principle means that you can have 2 patients with hardly overlapping sets of symptoms. And the heterogeneity becomes even more evident if you start reading what these symptoms are. So these can be weight loss or weight gain, insomnia, not being able to sleep, or hypersomnia, excessive sleeping, agitation, or on the contrary, psychomotor slowing. And so you can see that in principle, 2 patients with non-overlapping symptoms can get the same diagnosis. And the question now is why? So what accounts for this heterogeneity? What are the neurobiological mechanisms behind these different manifestations of depression? And can we use those mechanisms to offer more tailored treatment and improve treatment efficacy and general prognosis? And note that these types of questions I'm asking are valid not only for depression, but also for many other psychiatric disorders. The other difficulty in psychiatry is the lack of well-defined neuropathological and biological markers. Of course, this does not mean that mental illness doesn't cause real suffering. Think of depression, which is highly prevalent in the general population. And this also doesn't mean that all treatment is ineffective. What this means is that there is room for a lot of research and progress to be done. Finally, and also because of the second point, diagnosis mainly relies on clinical observations using diagnostic manuals, like the ICD-10 and DSM-5 that I've mentioned before, with diagnostic tests mainly being ordered as a means of differential diagnosis, that is, to exclude other pathologies, other diseases. So computational psychiatry has recently stepped in as a possible means of tackling these challenges. But what is computational psychiatry? So computational psychiatry, along with computational neurology and computational psychosomatics, are 3 burgeoning areas of research within translational neuromoduling, which itself is a more clinical and applied branch of computational neuroscience, aiming to translate insights from more theoretical or basic work to clinically useful solutions. And if you haven't heard of computational neuroscience before, so computational neuroscience is an expression that was coined in the 1980s that refers to a branch of neuroscience that uses mathematical models and abstractions of the brain to better understand development, physiology, aspects of cognition, and also diseases. Okay, so by now you might be thinking, what does all of this have to do with interpretability in healthcare? I mean, can't you in principle just take all your patient data, including reports and imaging, put it in a neural net and get some output? A neural net is a mathematical model after all. And the answer is that in principle you can, but that's not what I would argue for. Instead, a quite prominent approach in the field has been to construct what are called generative models based on biophysical principles. And this is an important point. Okay, so you might all know this already, but I was told that the audience is quite diverse. So just to be clear, a discriminative model is a model of the conditional probability of the target y given an observation little x, while a generative model is a statistical model of the joint probability distribution over y and x, meaning the generative model requires the definition of a prior and a likelihood function. And the generative model gives you the ability to generate new synthetic data points, which is also an interesting feature of these models. Okay, now back to computational psychiatry. A prominent generative modeling approach is dynamic causal modeling, or DCM, which was introduced in 2003 by Carl Friston and colleagues. initially for functional magnetic resonance imaging data, and then subsequently also developed for electroencephalographic, EEG, and also magnetoencephalographic, MEG data. In DCM, you construct a mapping from the activity of hidden states to observable measurements. So let me explain. Hidden states are things that you can't directly observe, at least not non-invasively. So this is, for example, the activity of ion channels that account for neuronal firing or the connectivity among brain regions. And what I mean by observable measurements are, for example, functional MRI or EEG time series, which you can non-invasively obtain from humans. So this mapping from hidden states to observable measurements defines a forward model. And the forward model is more or less involved depending on the DCM variant that you consider. So just for you to see one example, I've reproduced on this slide the equations of the forward model of the classical deterministic DCM for fMRI. And without going into detail, what I want you to note is that most model parameters are connectivity parameters that determine the coupling strength between brain regions of interest. And note that you can also have self-connections, so connections from one region to the same region. Okay, so much for the forward model. What you can then do is go the other way, meaning if you have observable measurements, you can try and estimate the probability distribution of the sufficient statistics of the hidden state, the hidden states. And you do this by fitting the data points you have, and in the end, checking the parameter values your model converges to. And this process is called model inversion and can be thought of as sort of applying a mathematical microscope. Now you can do something really interesting. So once you've collected your subject data and inverted your models to get subject-specific parameters, you can then use these parameter estimates as new interpretable features. And in this example, each square on the right of the slide represents one connection in the middle figure. So basically, you've created a lower dimensional embedding of the original data. And note that this embedding contains all of the parameters of the generative model. So on this slide, I've only represented the connection parameters for simplicity, but this doesn't correspond to the general case. So if you repeat this process for all your subjects, you get a new data set to which you can apply, for instance, a discriminative classifier, say a support vector machine, an SVM, to separate patients and controls, or much more interestingly, separate patient subgroups. And this approach of creating new interpretable features based on generative models of brain connectivity is called generative embedding. So this approach was used in quite a few publications. One example being this recent publication from 2020 from Fressle and colleagues, where they used a generative embedding approach to try and classify patients' clinical trajectories. In this proof of concept study, the authors analyzed fMRI data from 85 participants who enrolled in the Netherlands study of depression and anxiety, the NESDA study. And in case you haven't heard of it before, the NESDA study is a multi-site longitudinal study which started in 2004 and to date has recruited more than 3,000 participants. So for this study by Fressle and colleagues, inclusion criteria included a DSM-4, meaning DSM 4th edition, diagnosis of major depressive disorder, and patients had to have a baseline assessment as well as a follow-up of depressive symptoms over 2 years. In addition, all selected patients had to have participated in a so-called event-related emotional face perception fMRI paradigm. So what happens in this paradigm is that participants view color images of angry, fearful, sad, happy, and neutral facial expressions, as well as scrambled images. And participants were instructed to either indicate the gender of the presented face via button press, or for scrambled images, to press buttons in accordance with an arrow pointing either right or left. Perfect, so going back to the generative modeling approach, we can now assume we have the data. The next step is to perform model inversion to obtain subject-specific parameter estimates. But first, we need to define a connectivity model to analyze or to estimate the parameters. The thing is, sometimes you can't fully commit to one model, and your parameter estimates are conditional on the model that you use. So it's important that instead of defining just one model, you consider all plausible models. and this is called defining a model space. And that's exactly what the authors did. So they took areas of the brain network that mediates emotional phase perception and defined a model space based on models they considered plausible. The gray arrows indicate endogenous connections, while the lines in blue indicate modulatory connections, which are only triggered when certain stimuli appear. And so you can see that what varies between models is where the modulation by the emotional content of the image is supposed to take place. Okay, so you can see 6 models on this slide, and there is actually a 7th model that is not displayed here, where no modulatory connections were considered. Okay, so for each subject, DCM inversion was performed for all of these models on the slide, plus the 7th model, meaning you end up with multiple inverted models for each subject. Sorry. And the question now becomes, how do you take these different models and define a set of unique parameters for each subject? You basically need a principled way to average them. And the way the authors averaged these models was via Bayesian model averaging, where in this technique, each average parameter estimate represents a weighted average across the models considered, where each model contributes according to its posterior model probability. Okay, so now, equipped with averaged parameter values for each subject, the authors could then proceed with classification. And for classification, they opted to perform a binary pairwise classification using an SVM, a support vector machine, with nested cross-validation. And there were in total 3 classes that they wanted to predict, either a class of patients with rapid remission of symptoms, a class of patients with slow but gradual improvement of symptoms, and a 3rd class of patients with no improvement of symptoms, which basically went on to develop sort of chronic depression according to DSM-4 criteria. Okay, so these were the results. So when comparing chronic versus remitted patients, that's the leftmost column, classification was possible with a 79% balanced accuracy. And this result was statistically significant as assessed by permutation testing. Remitted versus slowly improving patients could also be discriminated. That's the rightmost column in the table. The balanced accuracy lay at 61%, but did not reach significance when corrected for multiple comparisons. Thirdly, chronic patients could not be differentiated from slowly improving patients above chance level. That's the middle column. And finally, another thing that the authors looked at was feature importance. And they determined that the most important or most predictive connections were the modulatory connections, in particular those mediating the influence of happy faces on the network. Okay, so that was an example of a study using generative embedding. Of course, generative embedding is really just an example of what you can do with these kinds of generative models. And I'm happy to discuss further methods either in the Q&A or in the Hangout later on. And in short, I hope I've conveyed to you why model interpretability is important in healthcare, how interpretability can improve accuracy by allowing probing, and hopefully I've managed to convey how carefully crafted models can potentially help us further our understanding of psychiatric disorders. And with that, I'd like to thank you for your attention, and I'm here to answer any questions that you might have. I'll also leave you with this little treat. And of course, I have a few acknowledgements to make. So thank you so much.
So thank you for your presentation. Before starting the Q&A, I want to ask again the audience to please make your questions in the YouTube chat. We'll copy them to the streaming platform, and we will do the discussion with the speaker. And I want to give the first question to Isabel. Ladies first.
Thank you. And thank you once again, Inês. I think it was a really insightful presentation. So jumping into the first question, let's say, isn't generative embedding highly dependent on the size of the dataset, meaning smaller datasets, 3, 15 replicates, wouldn't generate overfitted data points?
Okay, so I'm going to have to answer that question, I'm going to have to introduce a few new concepts. So it's not, so the way you assess overfitting in these kinds of models is by looking at a quantity that is called the negative free energy, which is also the quantity that you optimize when you're fitting these models. So what you do is you basically you kind of like derive a lower bound on the model, on the log model evidence, and use this negative free energy, which is actually the same thing as the evidence lower bound from the machine learning literature, to then, you use this quantity to then maximize your model evidence. And this quantity is actually subdivided into sort of two different quantities. It has an accuracy term, which is actually the expected log likelihood, and a complexity term, which is a KL divergence between the prior and the approximate, the prior and your approximate posterior. You need to make a few assumptions when you're fitting these models. And so, for example, one of the assumptions that is often made is that your posterior distribution is Gaussian. And this KL divergence then measures the kind of like the distance between these two and how much complexity you're adding to this model compared to the priors that you had. And so hopefully, this quantity should give us a sort of a good balance between accuracy and complexity. And you can then use this quantity to compare two models. And there's something called a Bayes factor. You can basically divide one by the other and then kind of like assess how much more probable a model is compared to another one. And so hopefully you would go around this problem of overfitting using this quantity.
Thank you.
Okay. Shall I let you? Okay. Do generative embedding features limit the expressiveness of the model? I'm not sure what you mean here. So yeah, I'm not sure what is meant here. Can maybe the person that asked this question? Yeah.
It was me, actually.
Okay. Yeah.
So yes. If you have features that are human understandable, or at least they have a causality relation between them, aren't we limiting the feature space that, for example, a neural network can explore to create a highly specialized model? I know there is a trade-off because the model will be less accurate, but I will understand what he has decided or how he has reached that idea. But how much does interpretability limits the accuracy of a model that has no constraints, right? He can think in any nonlinear regression or any nonlinear function that he wants to map the data without. It doesn't matter if the concepts or the features are connected in a physical possible way. It's how he does the math.
Okay, now I get it. And I do have a few things that I'd like to say to that. So maybe I'll address directly the issue of less accurate or less expressive model when you have an interpretable model. So I think that one person that I would point to is Professor Cynthia Rudin, whose work I quickly cited in my presentation, and she's working really intensively on this. And she published a Nature paper not too long ago, actually arguing against this sort of intuition that we have that interpretable models are less accurate or are less expressive than non-interpretable models. And she has a few cases documented where she basically obtained more or less the same accuracy. Of course, these things evolve over iterations, right? So if she started out with a perfectly linear model and it didn't give as much accuracy, then, you know, based on what the model was telling her, she could either basically make the model evolve to capture other features that she thought might be interesting. So that's the first point. I would say go check out Cynthia Rudin, everyone. She's an amazing speaker as well, so it's really nice to hear her talk. And I guess an answer to your question would also be, what do you want to do in the end of the day, right? So one of the projects I was also working on was in using these models to look at EEG data from patients that have a rare disease called anti-NMDA receptor encephalitis. It's a bit of a mouthful, but basically the NMDA receptor is targeted by autoimmune antibodies. And what we wanted to look at was whether the NMDA receptor parameters specifically were altered between patients and controls. And so if you manage to get a model that can express the difference between groups at this level of, you know, granularity and exactly in the parameters that you have, then, and that's almost like, that's an amazing diagnostic tool that you have. So, and you could also do all sorts of things afterwards. So yeah, that would be kind of like my answer to that.
I have a follow-up question regarding this.
Yeah.
As I understand, you can create more features to create a better model. Do you still hear me?
Yeah.
It appears my camera had a little spasm there, but it's okay now. So okay. Do you envision a scenario where you have so many understandable features that if you take, let's say, a week, you could understand how the decision was made, because you could derive all the relations between the features, but in the end, the derivation is so complex because you have being understandable doesn't mean it's easy to understand, just mean that
I can't hear you anymore. Am I the only one?
Yeah, no, I think we lost the audio from Mario.
Oh.
Yeah. Oh.
We can't really listen, but I think I can. I think I'm trying. I think I know what you're getting at. You're basically saying whether. Yeah,
No.
nothing. No. Yeah, so I can still try and answer the question I think he was asking, which is whether we gain a lot, if I understood him correctly, whether we in the end actually do gain a lot from these, from this interpretability, if the cost of then peeking into the model is much too high. And I guess in that case, I would argue it depends. It depends on the type of model you're using, and also depends on the type of technique that you're using. Because right now, there are a lot of feature importance sort of algorithms that you can use. There's code out there that runs pretty fast and that you can use to kind of immediately know which features are more important in your classifier's decision-making process, so to speak.
Sorry, can you hear me now?
Yes.
Yes. Okay. Sorry. Thank you for a reply. I don't think you hear me the last part, but the idea was, do you envision a scenario where we have so many features, although they are understandable in with respect to decision, it becomes so complex with respect to decision that you, even if it's a generative model with understandable features, you end up in a similar situation that does a discriminant model with non-understandable features. As the model complexity continues to increase and increase and increase, you end up in the same plateau.
Mm-hmm. Well, so I think that's an interesting conceptual exercise, but like these models have, well, put it differently, these models don't have like thousands of parameters. These models usually have at most, usually 150 or something parameters. and usually also less, especially if you're considering, for example, DCM for fMRI. Well, actually, that's not true. It depends on how many connections you use. And if you have a lot of connections, then you'll also have a lot of parameters, right? But it's different from a neural net. So you're not going to have like that dimensionality of number of connections. And hopefully, even if you're looking at the connections, and you end up having a lot of features that explain your classifier's decision-making process, you can still try and see whether, for example, you can identify networks in there. So you can still have, a lot of features, but then you might realize, aha, so this network is actually the network that is being involved, and kind of like summarize all of these features into one network that apparently is what is contributing the most to the classifier's prediction. Yeah.
Thank you. Going forward with the next question. So what do you think about bringing causality models into machine learning in healthcare? Is there anything new from neuroscience that could be implemented right now?
That's a great question. So again, I'm going to have to point you to two other people, because I mostly work with these models, but there are people who are looking who are looking specifically at causality. So if you want to look at causality in general, then you can look at Professor Matuis's work. She's at ETH Zurich. And someone who is also really interested in causality in neuroscience right now is Konrad Körding from UPenn. So I would point you to them if you want to know like how they're bridging or how they're bringing causality into neuroscience. More specifically, then it would be Körding's work.
Thank you. Next question. Do you know any open source project about MEL and mental health?
A lot of them. Yeah, so, okay, so there are a lot of toolboxes out there. So the toolbox that defines DCM models is called SPM, Statistical Parametric Mapping. So that's one. Then there are as well quite a few, I can't remember the name, but I know that there's another toolbox that is being developed in South Korea. I can definitely, I don't know who asked this question, but I can definitely like post the answer or post resources on Discord later on when I finally manage to get the name.
That is an optimal suggestion. For this type of question, we'll have the follow-up discussion in Discord. So please, all of the participants, ask them the tools and have this interaction directly with the speaker, because I believe Inês is not prepared to give a list of programs right now. But the good question, just we'll go to it again in the next phase. Thank you.
Yeah, that was a good catch, Mario. So let's go to the next one. Do you think that training with gradient descent is still appropriate, or should you bet in spiking neural networks?
That's so. Not sure how qualified I am to give a very specific answer there, because although I have done some work with neural nets, it's not one of my main focus. So there are probably other people who can give a better answer to that than me.
Sure.
We are reaching the last questions. So I ask you, if you have any question that you want to see in the stream, please ask it now. If you want to have a more personal interaction with the speaker, I will ask you to connect with us in Discord in a couple of minutes. But before that, as stated in the beginning of the presentation, good models depends on good data. How can we leverage the collaboration between both clinical and engineering communities?
Amazing question. So I guess I would go back to also one of the things that I said in the beginning of the presentation, which has to do with how we communicate. So if we want to foster collaboration, we need to stop this whole discussion or these whole claims of superhuman performance and just take them sort of as face value, because right now, even if it is superhuman in some areas, mostly the models are tested in vitro. And of course, transfer learning is a major issue in machine learning. And yeah, in the end, the medical doctor is still, well, the agent in this comparison that adapts better to new situations. And I mean, on the other side of things, we, as medical doctors, it also helps if we, we have to be open to these types of things, because I mean, like I said in the beginning, making a diagnosis and making a prognosis, or actually even offering a therapeutic option, is a highly complex problem. And when you have things like comorbidities coming into play, or patients have multiple drugs that they're taking, so a very complex medication, becomes quickly quite difficult to grasp how things are interacting with each other. And so if we can have like this extra agent that helps us and open up the idea to that, then that would be great. So I think to foster collaboration, we kind of like need to take this step back and create this common ground and this common goal that we want to achieve. And then engineers and clinicians would ideally collaborate, not only in creating good data sets that are both fueled by clinicians' domain knowledge, as well as engineers' knowledge of how to handle the data, and have them just go together through the whole process together. Also in the end, when the model delivers the results, to show them to the clinician as well and be like, what do you think of this? And based on this, develop multiple iterations of this process eventually. So yeah, that would be my main point here.
Thank you for your answer.
Yeah, that's really interesting. We're jumping into the last two questions. So regarding discriminative models, they typically work on a latent space, meaning that they learn it to model itself. That increases the accuracy of the model. How does a generative model cope with this?
I need to read this again. Typically work on a latent space. Who asked this question? Was it you again, or?
It was Mario, yeah.
Do you want to? Do you want to again maybe explain? Yeah.
Imagine a neural network, right? You can think of a deep neural network as each layer is a non-linear transformation of the input data to another space. You usually call a latent space with latent features, and finally you have a linear decision at the end. So you have n non-linear transformations that hopefully transform your data into something that is linear and easy to make a decision. This is in a discriminate model that does not care about reproducing the data. So if they make transformations, they change the shape of the input features into a field, into n dimensions where they are linear, or hopefully as linear as possible. Generative models cannot do that as efficiently because they won't model the probability of the model joint probability, not the conditional probability. So how do you cope with this?
Well, I mean, the generative model still has nonlinear properties to it, right?
Yes.
And I mean, depending on how you construct these models, you can also give a lot of expressivity to the parameters within the model. So, I mean, I don't see much of an issue here. That's what I'm trying to say.
The issue usually you can stack layers on a neural network without issue, because you don't care about doing the reconstructing the data set. You cannot stack, for example, Bayesian networks on top of each other, because you have to keep the properties of the probabilities same, and have to keep the distribution. So there is a limit to how a generative model can grow in complexity, or explode in probability calculus, and the model does not converge.
Yeah, I mean, a generative model can also be a neural net, right? And then you can stack as many layers as you want. But in this case, yes, I mean, this is not. You can expand the number of connections, but you can't expand a lot of the. Otherwise, you can't expand the model much. So that's a fact. The model is there, and then depending on which ion channels you want to model and how many sources you have. So a source is a brain region of interest that is a source of signal you have. That's going to define how many parameters you end up having in the end. And
I think I understand your reply.
Okay, yeah.
So
if not, then we can discuss in Discord, and maybe you can offline explain to me a little bit better where you're trying to get at, and yeah.
Sure. Thank you.
And we can go to our final question. And I believe so. It's a really philosophical one. So what do you think is the future of AI applied to healthcare in Portugal?
Nice. So what do I think the future of AI applied to healthcare in Portugal specifically is? So interesting. Well, I would hope that at least in the beginning, and this is not really specific to Portugal, but just in general, I would really hope that the AI or machine learning community would focus on certain lower hanging fruits. So things, for example, that could be easily automated and would already relieve the workload off of clinicians significantly. So I didn't put the tumor segmentation example there for nothing, because that would actually be something where radiologists will probably be grateful if the model works well. So if a radiologist is doing kind of like a follow-up of a lesion, they usually need to delineate the lesion and kind of like estimate how big it is and how it has evolved over time. And so if you have an automated way of doing that, then that just saves a lot of time. And so to have like these tools that can also as well be easily verifiable would be a really nice first step to already improve clinicians' working conditions. And then after that, maybe move on to more complex things. And start thinking about, having an aid in decision making in diagnosis, but that comes afterwards. So I would be really grateful if engineers out there would focus on these problems that seem kind of trivial but are actually super helpful for someone who is working in the clinic.
Yeah, that's really interesting, because during my bachelor's, I actually had to do something similar like that. So we had a computer vision project in which we're kind of trying to map brain tumors and try to detect them like automatically. So yeah, I think it would be great. So if you could like introduce that small things to help the professionals.
And still in imaging, like delineate cortex.
Yeah.
For example, as well, identify what is gray matter, white matter. That would already be helpful as well to calculate certain measures. Yeah.
Well, thank you, Inês. Thank you again for this presentation. I think it was really great and insightful. Mario, I don't know if you want to say something.
The thing is, and thank you not only for the presentation, but for being available to spend a little bit more time with us, speaking with all the participants. But before that, I'll have a couple of slides There is a call for proposals. Again, if you have done something useful, or if you know someone that has done some work in machine learning, data science, artificial intelligence, please apply using these links, and we'll evaluate your work and invite you for a follow-up webinar. Again, I ask you to fill the survey. It's really important for us. We are trying new methods of interaction. For example, our speaker was kind enough to make questions during the presentation for you to give your opinion. And we are trying Discord now to have a little bit more personal interaction with the speaker. And we need your feedback to know in which way we can improve even to greater extents. So this is a link for the network. You don't have to copy it right away because we'll have it a couple of seconds after the stream. But follow us in the Discord and go there to talk with us. Please do not turn on your camera, only your mic. There are a 25 limit of participants if anyone turns on their webcam. So for now, we are to include as much as possible, as much persons as possible. I will ask you for not to connect your camera right now.
Yeah.
And that's it. Thank you all for being here. I want to thank Inês for the presentation. I want to thank Isabel for helping and being the co-host, and all the people that are in the background doing everything that happens during the live stream. So thank you, and see you in a bit.
Yeah, thank you, Mario, and thank you, everyone. See ya.